Hello, good afternoon, everyone. I am Mansi. Today, we are presenting our preliminary results on the effect of aggregate shape and volume on concrete fracture, a mesoscale modeling uh, from the Department of Civil Engineering, NIT Rourkela. This is the overview of the presentation. Introduction. Concrete is a widely used construction material composed of cement, aggregates, coarse and fine, and water. It has a complex multi-scale and multi-phase structure across different scales and exhibits quasi-brittle fracture under various loading conditions. Interaction of various components at different scales govern the overall behavior of concrete. At macro scale, concrete is characterized as homogeneous material responsible for long-term durability properties. Moving down to a slightly lower length scale, at the mesoscale, the concrete can be classified as a three-phase material. At this stage, the evolution of microcracking and damage is associated with the initiation and propagation of cracks throughout the mortar region and the interfacial transition zone (ITZ) region, ultimately influencing the microscopic behavior. The figure 1 shows the real aggregate shape in a hardened concrete specimen and we can see that aggregates are randomly packed in the sample. The figure B shows the SEM image of aggregate cement matrix and ITZ with a magnification factor of 1000. And figure C shows the schematic representation of a concrete mesostructure. It can be observed from the figure 2 that ITZ is slightly more porous in comparison to the other two components, which makes it a critical failure site in concrete. Moving on to the cohesive zone modeling. Cohesive zone modeling is a phenomenological damage model that provides a simple and intuitive way to model the fracture in concrete. It is used in computational methods to simulate the initiation and propagation of cracks and materials. The damage is represented by using fraction separation behavior, and the CZM or cohesive zone modeling assumes that the fracture occurs progressively across an extended cohesive zone or the process zone ahead of crack tip, which makes it ideal for simulating concrete fracture which possesses a significant fracture process zone. Motivation for the study. As we know, concrete has a complex internal structure exhibiting quasi-brittle failure and post-peak softening, which makes it difficult to predict its behavior accurately. Hence, to comprehensively understand the macro-scale behavior, it is essential to understand the interactions between the major components of the concrete under the action of load. In this study, an attempt has been made to understand the effect of aggregate shape, circular, elliptical, and polyhedron, and volume on the crack propagation in concrete. The methodology. The fracture in concrete has been studied for a set of 3-point bend beams from the existing literatures. The geometry and loading setup is provided in the figure for a center-nosed 3-point bend beam specimens. The material properties are taken from the existing literature for different concrete components and is provided in the table 1. The initial cohesive stiffness parameter for opening and sliding mode is kept 10 to the power 6 for cohesive elements in both mortar-mortar interface and aggregate-mortar interface. However, the fracture energy for the latter is half as that of the former. The softening parameter alpha is again same for both the cohesive interfaces. The procedure for mesoscale modeling is explained as at first, the geometry of concrete mesostructure is generated using the Python scripting. The aggregates are randomly placed in the mesostructure domain. Then in step 2, the mesostructure is imported in Abacus CAE for finite element modeling and the material properties of bulk aggregates and mortar are defined, followed by an initial meshing of bulk elements. Then the input file is again exported to the Python scripting environment where the zero thickness 2D cohesive elements are inserted in the mesostructure. In step 4, the modified mesostructure is again imported in Abacus environment and assembled with the remaining homogeneous sections of the beam. In step 5, the meshing of remaining homogeneous beam structure is done, followed by the assignment of material properties, fraction separation damage criteria. In this study, quartz damage criteria, that is failure by quadratic nominal stress, is adopted. Then the suitable boundary conditions and loading parameters are provided to the model. The mesostructure generation. The aggregates are generated and placed in the mesostructure domain by take-and-place algorithm as suggested by Wang et al. This algorithm takes into the account of randomness and heterogeneity of the concrete components. The objective is to computationally generate and place aggregates in a repetitive manner until the target area is fully packed. For aggregate grading, the Fuller curve for size distribution is adopted. The placement constraints are enforced to ensure that there is a minimum distance between aggregates and specimen boundary, and the minimum distance is there between any two aggregates to accommodate mortar film thickness. These checks are to verify that generated aggregates should neither overlap with specimen boundary nor with each other. The placement process starts with the largest aggregate size segment and moves to the smaller ones. A random position for aggregate is generated, ensuring the aggregate is inside the specimen boundary and does not overlap with other boundaries. If any condition is violated, the aggregate is discarded and a new random position is attempted. The generation and placement steps are repeated for a given size segment until the remaining area is too small for another size of aggregate of that size. The process then moves to the next smaller grading segment and the entire cycle is repeated until the last aggregate of the smallest size is placed and the target volume or area is fixed. The flowchart for the take-and-place algorithm is shown in this figure 4. Moving on to the results part, the generated mesostructure. The figure 5 shows the generated mesostructure for circular, elliptical, and irregular polyhedron aggregates with a predefined notch. Figure 6 shows the irregular polyhedron aggregate geometry for volume fraction of 50%, 60%, and 75%. Figure 7 shows the mesoscale geometries for geometrically similar beam samples designed for the experimental data of Bhowmik and Ray. Insertion of cohesive elements is done in two stages. First, the mesh data from the Abacus input file is passed into an Python environment to identify the common nodes in mortar and aggregate sets. The shared boundaries between mortar elements and aggregate mortar elements are then identified and all the shared nodes are duplicated with same coordinates as the original. In stage 2, the elements next to each other are identified and zero thickness cohesive elements are inserted, connecting the original node on one side to corresponding duplicate node. Separate sections for mortar cohesive elements and aggregate mortar cohesive elements are made and corresponding material properties and damage criteria is assigned. The file is then imported in Abacus for further modeling. The FEM modeling of mesostructure. The 2D FEM of a North concrete mesostructure in Abacus is shown in the figure. The dark green polygonal elements represents aggregates and the blue part represents the mortar. Three-noded triangular plane stress TPS3 elements are used for the meshing. The element size is kept as 1 mm and the zero thickness elements have been inserted along the boundaries of all triangular elements using Python script. The figure 9 shows the finite element meshing of the aggregate, mortar, and the corresponding cohesive elements in the ITZ and the mortar matrix. The model assembly figure. The remaining homogeneous left and right parts of the 3-point beam is assembled and coupled to the generated mesostructure using tie constants in Abacus. The mesh size in the homogeneous region is varied from 1 mm near the assembly to 15 mm towards the end. The displacement control loading of 0.2 mm is provided at the top. The load CMOD curve shown in figure 11 shows a comparison of load CMOD data from the experimental result and the numerical simulations for small, medium, and large specimen. The result shows a fair agreement in the curves with maximum load and factor energies being comparable. suggesting that mesoscale modeling can be used as a reliable tool for simulating large-scale engineering structures. Concluding remarks, a two-dimensional mesoscale model consisting of mortar, aggregate, and interfacial transition zone has been modeled using cohesive elements in finite element method. The results of parametric analysis reveal that variations in aggregate content strongly affect the macroscopic stress strain or the load CMOD behavior and the failure mechanisms in the concrete. The initial elastic stiffness increases with higher aggregate volume content. However, the peak load decreases since a larger aggregate fraction introduces more cohesive elements into the ITZ region, and the properties of cohesive element in ITZ is assumed to be weaker than that of mortar. For identical volume fractions, the mean peak stress of specimens with circular or elliptical aggregates is slightly higher than that of polygonal aggregates. This is again can be attributed to the increased aggregate mortar interfacial elements area. The side effect in geometrically similar notched beam has been successfully reproduced through the model. These are some of the references used for the study. Thank you for your attention and any questions?